So, chapter 16, so gas, air, liquid solution, salt, sugar water, salt water, solid solution. Quartz would be a compound too, because silicon and oxygen are fixed. The composition can't vary. And if you have a fixed composition, it's not a mixture. Mixture is defined by having a variable composition. This is back in chapter 1 though, or chapter, was it 1? One of those chapters, beginning. Solid solution, an example of a solid solution would be sterling silver. Does sterling silver look uniform throughout? Yeah, sterling silver looks like it's a pure compound or a pure element. And it has 92.5% silver and 7.5% copper, but is that fixed? For example, could there be a little bit extra copper and a little bit less silver in that? Yes, there could be. And so there's going to be some it's not fixed like water. You know, could you have a little bit extra hydrogen and a little bit less oxygen in water? Is that possible? No, it's not possible. You know, because the composition's fixed, 2 hydrogens, 1 oxygen. But sterling silver, of course you don't want less silver and more copper, you know, because copper is a lot cheaper. But it's the same thing, like 18 karat gold versus 14 karat gold. You know, what would you rather have? You know? Or 24 karat gold. You know, and so those are brass. You know, there are lots of different compositions of brass. And so brass, is that a pure compound? Is it fixed ratio of copper and whatever else? Tin, wood and brass? No. And so solid solutions would be alloys. Like that, alloys. So we go through this. These particles, the solute particles don't settle. Otherwise we call it a suspension, but we don't have to worry about that here. 2 solutions made up of the same substance may have different compositions, yeah. The sugar water can have multiple compositions. It can be concentrated or it could be dilute. And so if you know this, then these types of problems are just reinforce that, you know, reinforce that. So our focus is, you know, what is a solution? Can you give examples of a solution? Does it make sense? What are the parts of a solution? Well, we have 2 parts, the solute and the solvent. And so the homework there is just to reinforce those. If you don't need much reinforcement for those, just skip that. You know, so you don't have to know every example of a solute and solvent. We don't want to memorize it. We just want to get a good feeling. And so to get a good feeling or to build up some comfort level, you do as many examples as you need. And so my studying, the way I would study is very targeted. Anything I felt uncomfortable with, I'd do every single problem. Anything I felt comfortable with, I skip around. The same thing goes with the reading. When I read the book, I don't read every page with equal weight. The stuff I'm weak on, I read in depth and slowly. The stuff that's not so difficult, or the stuff that I feel comfortable with, I skim or skip entirely. And that way I can keep up with the reading. Otherwise the reading becomes too time consuming also, because, you know, I've timed it before where I've spent, you know, it's like I was taking an English literature class. We had 1,000 pages of reading. But 1,000 pages of reading, I timed it, and I could read per page. It wouldn't take that long. Versus I was also taking an engineering course at the same time. So I figured for every 100 pages of literature, I could read 1 page of engineering. It was crazy, the ratio, because that 1 page of engineering, I'd have to do sample calculations, and then I wouldn't understand it, so I'd have to go and search for other sources to help me understand it, because it's so confusing. And then they skip a lot of steps. In engineering, you know, they jump from this to this, and you go, how did they jump from there to there? And so you have to go back and kind of reverse engineer their whole calculation, you know, and so it's very time consuming. And so anyway, what you want to do is you just want to do it. Are you comfortable with this? If you're comfortable with this, then yeah, just kind of skim through that. This is a more solute solvent. This is copper 2 chloride in water. Talked about that. Concentrated versus dilute. I don't think we need very many examples of this. You could have concentrated sugar water or dilute sugar water. You know? And so, feeling comfortable so far. You know, this is dilute. You can see the color is a lot lighter. This is more concentrated, it's a more deeper blue color. You know, but color can be affected by the lighting as well. And so this is difficult to see. But there's other evidence that this would be more concentrated because there's the extent of reaction is a lot more. So solubility, you know about solubility, and so what we want is we want some problems dealing with solubility. And so I go back and look at the homework here, because I talked about the two definitions of solubility. What were the two definitions for solubility? One was qualitative, the other was quantitative. So there was one question here about solubility. A saturated solution is at its solubility limit, so it is concentrated. Not necessarily. Was that the answer in the book? Or was that your answer?
The answer was 4.
Saturated solution is at its solubility limit, so it is concentrated.
That was the choices.
Oh, that's a choice?
Yeah.
Was that true or false?
I think it's 4, that a concentrated solution is a saturated solution. Pointing out the okay. I think I checked the first one. Is there any more to that problem?
Let's take a look at this problem. Well, we need the. I don't have the complete text of the problem, so it's something.
The distinction between two.
All right. Oh, okay. That's fine. I missed that. Point out the distinction between the sometimes confused terms. A saturated solution is at its solubility limit, so it is concentrated. Is that true or false? Yeah, it's not necessarily true, therefore it's false. And it might be concentrated, it might not be concentrated. It depends on how soluble it is. And so some things are highly insoluble. So let's say I'm going to saturate my vinegar with oil. You know, and does that mean the oil's concentrated in the vinegar? I'm going to pour off the excess oil. No, because oil is immiscible in vinegar, so it's not. And so what I do is, I just make sure I know the definitions of solubility. What do they mean by solubility limit? What's that mean? That type of stuff. And then I'd look, because I would have to look at what was said in class regarding this. A concentrated solution is not necessarily saturated. That's true. If something can be highly concentrated and not saturated, there could still be room for more. A concentrated solution contains a relatively large amount of solute. That's false. Or is that true? That's true. I take that back. That's
These
true.
are all statements that they said to fulfill the answer to the question. This is their answers.
Okay. A saturated solution cannot hold more solute. That's true.
So these are the 4.
These are the answers, but this first answer I have a problem with. It's not necessarily concentrated. A saturated solution is not necessarily concentrated. So the first one is a little bit. This is okay. So this is more saturated, unsaturated, and supersaturated, but we're talking about solubility. That's relative to its solubility. That solubility is quantitative. And so in stating solubility, all right, it goes on to solubility, then it goes to miscible, and then we're in the next section. And so there's a disconnect there because there's something that was important that's missing from the homework set there that I thought was important. And that is, there are two definitions of solubility. What are they? And so during that time in class, I thought that was important. So, but if you just studied the homework, then
Take the homework, compare it with the notes.
right, you compare with the notes, and the same thing with the reading. You categorize, and then if the homework doesn't do it, and if the reading doesn't do it, then you search for other sources. Because if there's something that's confusing in the lecture, then you look for clarification anywhere you can. If there's something confusing in the reading, then you look for additional help or clarification, or something confusing in the homework. But so far, even though 153 problems is still not enough because it didn't cover the two definitions. Does anybody remember the two definitions of solubility? The quantitative definition and the qualitative?
So it pertains to solubility rules.
Yeah, it pertains to the solubility rules. The solubility rules are the qualitative one. It's either soluble, I said S, insoluble, I, and SS. I wrote it on the board. SS means slightly soluble. And then I told you this is totally not black and white. This is totally gray. This is arbitrary. Somebody came up with this number arbitrarily. What was that number? 0.1 moles per liter. It's a little arbitrary number. And so that's a qualitative, if it's more than 0.1, if it's less than 0.1. And then I'd be looking for homework that digs deeper into that, but there isn't. It's only the solubility chart. And the solubility chart, it doesn't give us the numbers. The numbers are the solubility, the quantitative definition. And so that's a case where, the book's homework didn't quite dig into it, and so you have to look for additional homework to help you understand that particular concept. But yeah, this is, Richard, how much time did you spend on this? Just curious.
I didn't have a little time.
Just work through
I was
it.
so interested because it's my major, chemistry, AA degree, so I just kept going.
That's good. It's extremely helpful to do all of them. Just to write them down, write the answers. A lot of instructors say no. Don't look at the answers. Don't look at the solutions guide. Do it yourself. I used to do that too. I would not open the solutions guide. Even though at UCLA, when I was a student there, they had the complete solutions manual. They have the answer guide to every single question in there. They didn't care, or at least all the classes I took, they didn't care. Because the exams, of course, they made like a notch harder than any homework problem. And so you really needed to do all the homework because to prepare yourself for the test. The test was going to be harder. And so anyway, it was very helpful to do. So I would work on one homework problem. I'd work on it, and pretty soon, 3 hours gone by, and I haven't even completed one homework. Then it's worthless. It's worthless because I didn't see. It didn't teach me anything. It's like a forest.
It's like to do it.
Right. You're out sent to the forest to study all the trees and plant life and whatever, and you spend your entire 1 month studying one tree. you aren't going to know anything about the forest, right? And so that's the same thing. If you just study one problem because you spend all your time studying that, it's not going to be very helpful. So if you have a limited amount of time, you try to see as much of the forest as you can. And so this is why we take a rapid walk through the forest, which is doing all the homework problems. But your rapid walk through the forest so you see the breadth of plant life out there. Otherwise, your focus or your universe or your world is very narrow, and you don't see much. And so what you just did there is very good, you know? But still, it's a lot to, you know, you can't log everything because you do have a limited amount of time. So what you do is you don't memorize each and every plant and what the height of each plant is and how many centimeters width, how many centimeters height, you know, the age, this type of stuff. You don't log, you just log generalized patterns, you know, and generalized trends. So we try to summarize it. And so the next step is after writing this down, you thumb through it and you look, okay, these are all kind of the same thing. What's the net result? This is what I said. What's the take home? You got to make your own take home message. From this series of problems, solubility problems here, what's the take home message? One, you need to know the definition of what a solution is, right? Two, you need to know what solubility is, you know, unsaturated, saturated, supersaturated. Three, well, we just moved on to the next section, which would be things that impact, you know, solubility. I talked about a number of things that impact the solubility. Temperature is one. Pressure is another. You know, that impacts the solubility of given material, but what impacts solubility, like some substances, are soluble, others are not soluble. That's a different story. And so, you'd look at something like this. So in this case, it's a little bit tricky because we're looking at a miscible and an immiscible substance. And so really, since this is infinitely soluble, octane and carbon tetrachloride are very, very alike in terms of intermolecular forces. So it's like mixing water with water. It's mixing oil with oil. So when you mix oil with oil, it forms what we call an ideal solution. They're infinitely soluble in one another. So water would be infinitely soluble in water. Oil should be infinitely soluble in oil. Oil and oil. However, oil and water don't mix. This is immiscible. And so the increased solubility, we look at other factors like temperature and whatnot. But when we're dealing with miscible and immiscible, those are kind of irrelevant here. And so this jump, you know, because when I was talking about saturated, there's one way to increase solubility, that's temperature. And then I had to jump way up here because this is sodium acetate. And we jumped to this slide here. This slide shows the solubility of salts. You know, and the take-home message is, yeah, we don't want to memorize each trend here, but the overall trend is what? You know, the take-home message from this is not to memorize the chart, you know, with one exception. The way I memorize this is that solubility increases with an increase in temperature, with some exceptions, with very few exceptions, let's say. And so solubility increases with increase in temperature. So in hot water, it's more soluble, and cold water, it's less soluble. Then I went back to this, saying this is how we make supersaturated solutions. There are two ways that I showed how we make a supersaturated solution. You guys recall? Two ways to make supersaturated solutions. one way is to heat it up and then cool it down. But when you cool it down, it might, actually this is perfectly clear. This is before they put the seed. Before they put the seed crystal in, everything is still in solution, but now it's cooled back down to room temperature, which means the solubilities drop. And the reason why it doesn't crystallize out, all the excess solute that's dissolved in there, is because of what? Well, the temperature is cooled down, so it should come out. It should precipitate out of the solution, but the reason it doesn't is because it starts with an N and a C. It wasn't in the book, but But, we should have it written down at least. How can we make a supersaturated solution? Why do supersaturated solutions form? Well, we're adding a seed crystal because adding a seed crystal is a lot easier than they seed like cloud, they seed clouds to try to promote rain formation because of this process.
Starts with a C.
Starts with an N.
Starts with an N.
Yeah, the thing is to prioritize your studying. When you prioritize your studying is what's the most important for the test. The most important for the test is not necessarily what Krakalici thinks is the most important, or not necessarily what the PowerPoint author thinks is most important, or the homework. I don't know if Krakalici wrote all the homework problems thinks is the most important. Out of 153, all of them aren't going to be of equal weight, and it depends on the bias, the personal bias of the instructor. That's what you need to focus on, the ones that the instructor is biased toward. And so, the instructor might be biased towards something.
It's comparable to the lab.
Yeah, the lab too. The lab, a lot of labs are edited. Some of the experiments are edited out. So some parts might change.
Or comparable to the equations you put on the board.
Yeah, this is something that. The role of the seed crystal or the role of Mentos. Remember Mentos? The role of Mentos, although I didn't get a great video for that, but the role of Mentos was to do what? To promote. The role of the seed crystal was to do what?
Nucleation.
Yeah, nucleation. The reason why we can form supersaturated is because nucleation is difficult. Some things are easier to nucleate than others. Something like sodium acetate is difficult to nucleate. So if you just leave this alone, it's going to take a long time for a crystal to nucleate. In order for a crystal to nucleate, the sodium ions and the acetate ions have to come together in the perfect position with low enough energy. You don't want them to bounce off each other. And if they're just slightly misaligned, they aren't going to form a crystal. They have to be perfectly aligned to form a crystal. And so that process is sluggish because the acetate ion is kind of a complicated shape. It has a trigonal planar carbon and a tetrahedral carbon. There are 2 carbons there. And so it has a complicated shape, making it hard to crystallize. So they drop a seed in here of sodium acetate, and so that growing can occur, and this crystal just grows bigger and bigger. Because once we have a crystal there, then the ions can attach in the correct positions. And so those are words that might, pop up on the test because like nucleation and crystallization, but those aren't on the homework. And so you could, or in the book. And so what's more probable, finding something, that's obscure in the homework or finding something that was talked about in lecture? What's more probable is something that was talked about in lecture. And so this is why, if something's obscure in the homework and I didn't really talk about it much, and skip it, you can just move back to this. Although this is important here. Let's take a look. Which of the following solutes do you expect to be more soluble in water than in cyclohexane? Well, first, water is polar or nonpolar? Water is polar. Cyclohexane is nonpolar. And so, as we go down the list, it's just light dissolves light. Now, I didn't give very many examples of this, but this is important for solution formation, light dissolves light. And so we saw that the octane with carbon tetrachloride, how those mix, and then water with. Did I give an example of miscible? What did I say is miscible in each other? Oh, okay. Did I, before that, I should have given you the example of methanol and water. Methanol and water. No? Okay, methanol and water, ethanol and water, miscible. Well, when you get to butanol, butanol is starting to become insoluble in water. Pentanol is pretty much immiscible in water. But anyway, formic acid is polar, so that should be soluble in water. Benzene's nonpolar, so that should be more soluble in cyclohexane. Methylamine, we'd have to have the structure of that, but it's like ammonia. This is like ammonia. There's nitrogen bonded to hydrogen. It's soluble in water. Tetrafluoromethane is like carbon tetrachloride. This would be carbon tetrafluoride or tetrafluoromethane. It's the same thing. So, we go through that. Here are the, you did the Lewis structures? So we can see.
Which ones to memorize?
None.
Okay.
You don't memorize, as long as you know how to generate the Lewis structures, you're okay. Were you able to make these yourself, or were these given in the problem?
Given in the problem.
Oh, given in the problem. Normally what I would do is I'd just give you like a formula, CF4. If I gave you CF4, that's tetrafluoromethane or carbon tetrafluoride, or CCl4. You'd have to determine it. But this, you just want to scan this and take a look at what types of intermolecular forces. So for example, HF, well, it's hydrogen bonded fluorine, so that's unusually big dipole, or a regular dipole, or a temporary dipole in HF. HF would have an unusually big dipole because whenever hydrogen is bonded to fluorine, oxygen, or nitrogen, we have the capability of hydrogen bonding. Hydrogen bonds are important, especially in water. And so HF is very soluble in water, should be. This one too, methylamine, should be soluble because we have nitrogen bonded to hydrogen here. Ethanol should be soluble in water, hydrogen bonded to oxygen, like in the H bond. Glycerin should be very soluble in water. We have 3 alcohols in glycerin. Glycerin should have very strong intermolecular forces. In fact, it's very viscous, syrup-like, has a high boiling point for an alcohol, high heat of vaporization, high surface tension, low vapor pressure. So, compared to benzene is a lot less in terms of intermolecular force strength. And so we just give a perusal to those and see. On opening a carbonated beverage, so we were talking about this earlier.
So that compares with the notes, so.
Yeah, that compares with the notes, so you just make sure you understand that. The notes kind of get mixed up here because the PowerPoints don't exactly go in order. But we talked about solution formation here. So, for example, dissolving versus crystallization. Oops. Let me go back to this. Dissolving, crystallization, and on. All right, so what we'll do is we'll just do a review then. Since you put in the effort for doing the homework, we'll take a look at the problems here. Sure. So this is the CO2, and then we go into section 16.5, solution concentration, percentage concentration by mass. And so here we have a solution of calcium chloride in water. We could figure out the percentage by mass if we know how many grams of calcium chloride and how many grams of water. So that's what you're doing here. You get 2.78%. How many grams of ammonium nitrate must be weighed out to make 415 grams of 58.0% by mass solution? That's very similar to the problem we did in class, so that's important there. Both these problems are good here. I guess that's it for percentage. So something's missing there. What's missing? What's missing in that particular? Because now we're on section 16.6, so we're missing from something in 16.5 that I talked about. It's also missing out of the PowerPoints. If we compare it to the PowerPoints, it's missing as well. So when we're talking about composition of mixtures, we have percent by mass, right? And then we went on to molarity, but there's something missing from there. So just take a look at your notes really quick. We'll be right back. Did somebody find it? We'll just look at the, rather than look at the answers, we'll just look at the questions. List. And so we're in section 16.5, solution concentration percentage of concentration by mass. These two are good representative problems. These black ones are parallel problems to those. You do the black ones if you need additional practice. One wasn't enough. So sometimes I do the black ones as well. But the answer's not there, you know. The answer's not there, so you had two choices. One, you either learn it well enough so that you're confident that you're doing it right, I'm sure I'm doing it right. Or two, you try to find the answer to that. See some. How you try to find the answers, you compare your answer with your friends, your neighbors, your peers, and see if they got the same answer. If they got the same answer, then yeah, you can have more confidence. If they got a different answer, then you try to figure out who did it right, who did it wrong. So we have study groups like that. What we do, And so, but do you know what's missing? Well, the reason I'm saying this is because I spent quite a bit of time. It depends on it. You can also weight things by how many minutes I spend in a lecture talking about it as well. And so I'll tell you what's missing. What's missing, and nobody has it in their notes? No? Molality comes later. Molality's in the next section. About 16.6. Not next section. 16.6 is molarity. Molality is over here. No, it's in the percent. It was in the percent composition by math. Basically, I said that percents are useful for more concentrated, but when you get to highly dilute, then probably percents aren't as convenient. We would probably rather use what? Nobody? Parts per million. That's it. And so I spent some time talking about parts per million, parts per billion here. And so you might want to spend a little bit of time, looking at parts per million and parts per billion, because that's actually the second time I talked about it. So you could go back to the first time I talked about it. But if we have very dilute solutions, it's a lot easier using parts per million. It's like, okay, how much water did you drink today in microliters? Okay, how many microliters of water did you drink today? That's pretty inconvenient. I don't want to use microliters because I drank a lot of water, right? So I'd rather say milliliters. How many milliliters of water did you drink today? Well, it's the same thing, if you're like the size of an ant, then milliliters be like a pool-sized volume of water for an ant, and therefore you wouldn't ask an ant how many milliliters of water, you'd ask them how many microliters of water. And so it depends on this. I mean, if we have very dilute solutions, we might use something like parts per million instead. And so that's something that, that's something extra that, you would think, well, the instructor mentioned this, so maybe I should look into it. Well, it's not in the homework, so maybe I should search. Well, you've got to search back in your notes for that. We talked about parts per million so long ago. But anyway, it's 16.5. So percent by mass, and then we went on to molarity. 16.6. The formation of solution, formation of saturated solution, factors that determine solubility, factors affecting solubility, so determining solubility versus affecting solubility. Gas pressure and temperature. Okay, and then, yeah. And so what I try to do at this point is I try to come up, with just a mental summary of this in my own words, the definition, and then 2, light dissolves light, and then 3, you can increase or decrease the solubility by adjusting certain variables like temperature or gas pressure. And then 3, the dissolution of the solubility process. We have here dissolving, crystallization. When the dissolving rate and the crystallization rate are equal, dissolution, which is dissolving, crystallization, or precipitation, then we have a saturated solution. So, I just say unsaturated, unsaturated, saturated. We could get supersaturated. This is all at a given temperature. If I increase the temperature of this, what do you think? Would the solubility go up or go down? It should go up because most solids, the solubility goes up with just a few exceptions. And so solubility should go up. And then if I cool it down, the solubility should go down and the excess should crystallize out, but the excess might not crystallize out because of, or if I just do this, if I leave this at this temperature and then cool it down to a lower temperature, then the excess should crystallize out. But it may not crystallize out so easily because we need seed crystals. There'll be plenty of seed crystals here, because lots of extra crystals. But if there are not a lot of extra crystals, or if there are no extra crystals, you'll see. So I try to add little notes to the slides like that. Okay, then we get the percentage concentration by mass. And then I'd repeat all these calculations here. Because before I do the homework, I would repeat all the calculations that were done in lecture. And so the steps would be this. When I would study is I would review what was discussed in lecture, make sure I didn't miss any concepts. If I did, I would add those in, like here. But these were my notes, and if these were my notes, and the instructor did talk about ppm, I just added ppm. And write a little bit about it. Okay, then I redo all the calculations, But this was an example calculation we did in class. I'd redo this from scratch to see if I could do this. This one I wouldn't look at the answer. I try to do this without looking at the answer. So redo the calculation. Well, this calculation is very similar to a homework calculation. So if I felt comfortable with that calculation, I would skip the one in the homework, which is a percent by mass calculation. And so this calculation is the same as calculation number 33. Calculate percentage concentration by mass of the solution prepared by dissolving 2.32 grams of calcium chloride. So we just go from grams of calcium chloride to moles of calcium chloride, and then 81 grams of water. So altogether we'll have 83.32 grams of solution. We calculate it using the same method. So what I would have done is I would have logged, how did we solve this? Well, let's go back to this. This is the exact same problem kind of thing, 42.3, this is a percent by, so 42.3 grams of solute, 125 grams of solution. So the total would be, you add up those two and the percent. So it's the exact same problem as 33. I would do 33 if I needed additional practice. So after doing this one, I was a little shaky. I do spend time on 33. you're to prepare 2.50 times 10 squared grams of 7.00% by mass sodium carbonate solution. What mass in grams of sodium carbonate and what volume in milliliters of water do you use? So I'd have this problem mentally cataloged, and then I'd go back here and look. At the homework, and look at 35. Well, this is the exact same problem. How many grams of ammonium nitrate must be weighed out to make 415 grams of 58.0% by mass solution? So if that's 7.00% by mass solution, I was still not confident and still not comfortable. I do that. If that 7.00% by mass problem was okay, the one we did in class, then I'd stick it. You know. Particular problem. So that'll cut down the number of problems by quite a lot. And then we go on to molarity after this. So this is the last one. I did some ppm problems. Examples of ppm. Just moving the decimal point over. That's all I did. So I would look at those and make sure I understood what was I doing when I was moving the decimal place over, you know, in that case. And then if I didn't understand that, then I'd look for that in other sources. You know. And then we went to molarity. Do you know the definition of molarity? You know, that's important. Okay, if you know the definition, then we should be able to calculate the molarity. Okay, calculate the molarity of a solution made by dissolving 15 grams of sodium hydroxide and diluting it to 100 milliliters, 36 figs. Okay, I go back through this and I do this problem myself. And then, you know, when I'm doing the homework, let's take a look. Good. The first problem, molarity. Potassium iodide can be an additive in iodized table salt. So they put a little bit of potassium iodide in the sodium chloride here. Calculate the molarity of a solution prepared by dissolving 2.41 grams of potassium iodide in water and diluting it to 50.0 milliliters. So that has nothing to do with this. We're just taking pure potassium iodide and dissolving it in water and diluting to 50 milliliters. So we have a total solution volume of 50 milliliters. So 2.41 grams of potassium iodide, 50 milliliters of water. Here, 15 grams of sodium hydroxide. Well, it's not potassium iodide, it's sodium hydroxide now, and diluting it to 100 milliliters of water. The same problem, basically. So skip or do it, you know, depending on your comfort level. Okay, then we went on to molality. So I just gave one example of molarity calculation. So you look at what other types of molarity problems might we encounter. And so when we look at the rest of the homework, that gives me a broader breadth of what other types of molarity calculations could the instructor potentially ask. And so let's take a look. And so there are a lot more problems in the molarity. In the percent by mass concentration, there are only a total of 4 problems, 2 blue, 2 black. In the molarity, there are a whole bunch of problems. So I'd be very curious, you know, what types of variations. So looking at this one, a student dissolves 18 grams of anhydrous nickel 2 chloride in water. So, you know, automatically what I do is I catalog, okay, they're giving us the grams of solute. Well, they give us the grams of solute in the instructor example, they give us the grams of solute in the previous homework, and they give us the grams of solute here. So we just convert grams to moles, so there's no difference there. And dilutes to 90 milliliters. Well, it's the exact same problem. The first sentence of this is the exact same problem. So what's different? He also dissolves 30.0 grams of nickel 2 chloride hexahydrate in water and dilutes it to 90 milliliters. Okay, so this is a repeat. So we're making 2 separate solutions, but exactly the same thing, exactly the same calculation. And then we're just comparing which one has a higher molarity. All right, so that, you know, it's a little bit of variation, a little bit more work, but the exact same calculation. Large quantities of silver nitrate are used in making photographic chemicals.
find the mass that must be used in preparing 2.5 milliliters of 0.058 molar silver nitrate. Ooh. Now this one is different. This one, either I ignore it because the instructor didn't talk about this, or I take a look at this one. But this one does. This one we're given the molarity and we're given the volume. We just need to find out the grams. Now, the reason why the instructor skipped this one is because this is the first step in stoichiometry. The first step in stoichiometry is to take the volume and the molarity and calculate the moles. So from volume of the mixture and the molarity, we can get the moles. And so we have the volume and molarity. So liters times moles per liter gives us moles. So we have moles of silver nitrate. All we have to do is do mole to gram conversion. Then we're done. So this would be a little bit of dimensional analysis here. But that comes later, so I didn't really talk about this yet because we're doing liter to mole conversion later. So we go milliliters to liters, liters to moles, moles to grams. It's kind of a stoichiometry, but it's not a chemical reaction. It's just dimensional analysis here. Potassium hydroxide is used in making liquid soap. How many grams would you use to prepare 2.5 liters of 1.40 molar potassium hydroxide? Well, it's the exact same problem, except we don't have to do a milliliter to liters. We already have liters. And so if we're given liters and molarity, we can get the moles. If we get the moles, so liters to moles, moles to grams. 45, what volume of concentrated sulfuric acid, which is 18 molar, is required to obtain 5.19 moles of the acid? And so this one's different, but this one is again dimensional analysis. So I would be logging these because I would be thinking, especially like I said, at UCLA they give the complete solutions manual, so you're always looking for something different than what the homework presents, and so you want to know every single variation that's found in the homework and then just tweak it or try to find other ways. And so I would be cataloging these in my mind. Okay, this is this to this to this, and then this problem we got moles, and so we want to go from moles to we have 5.19 moles, and so we want to go to liters. If we have 5.19 moles and we want to go to liters, well, we're going to have to flip the molarity upside down. If we flip the molarity upside down, because molarity is the molarity there, 18 molar, 18 moles per liter. And so if we flip it upside down, then the moles cancel out. It gives us liters. And so that was the little variation, because all the others we use molarity as is, moles per liter. This one we have to flip it upside down to get the liters. That's the first sulfuric acid. So I could put in sulfuric acid there. Concentrated sulfuric acid is 18 molar. That's how you buy it from there. So if we want 5.19 moles of acid, that's although this is not that common a problem. Usually we do it stoichiometry where we add more steps to it. 47, if 0.132 molar sodium hypochlorite is to be the source of 8.33 grams of dissolved solute, what volume of solution is needed? So this is a little bit different. The only thing that's different is rather than give us moles, they give us grams. So we'll have to do a gram to mole conversion and then mole to liter conversion. And so we need one extra step here. The one extra step is grams to moles and then moles to liters versus a straight mole to liter conversion. And so that was okay. That was a little bit of variation. So far these aren't too repetitive because they're all giving me a new twist, on the problem. And those new twists, I like them because I see, how many twists can you come up with? And there's only like a finite number, and hopefully you see all of them. If you see all of them in this section, then you're more than well prepared for any kind of problem that you can be hit with. despite its intense purple color, potassium permanganate is used in bleaching operations. How many moles are in 25 milliliters of so this is a repeat. 51 is just like 43, which is just like 41. So there's no new twist here. This is the exact same problem as we saw before, so skip it. We're given volume and molarity. If you're given volume and molarity, you get the moles, right? Except the only thing is, what was the new twist here? There's no new twist. That was exactly the same, so I kind of skipped that problem. The only thing that that could be useful is that potassium permanganate is like grape juice. You know, people think of potassium permanganate as grape juice, but you'd never want to drink this because it's a powerful, what? Potassium permanganate is a powerful. It's in the top 5 of one of your lists. You know the top 5 of your list? It's the top 5 of one of your lists. It's okay because it's not on this chapter, but it's coming up. The only reason you know it's in the top 5 of one of your list is not because you memorized it, it's just because you've seen it many times before. If you've seen it many times before, then it's not necessarily sitting there and rote memorizing it. It's just, oh, I've seen that before. Or I've seen this before. And that's how we learn a lot of the chemistry. Oops. I'd never memorize this. You know, I'd never memorize number 1 fluorine, number 2 ozone. Never memorize that, because I mean this list is abridged. It's not comprehensive. Number 1, number 2. You know, it's not work. But what you do is you just kind of catalog. You know, what are the powerful oxidizers? Their general thing. And so, you know, reading this list, okay, fluorine, ozone. This is a strange one. Disulfate, that's hydrogen peroxide, and this is permanganate. Permanganate, I remember because permanganate's in number 5 here on this list, but on another list it's not. You know, on the other list it's lower or higher depending on how comprehensive that list is. And the permanganate, I just remember powerful oxidizer. And that just comes not through memorization, that just comes from reading the list. What I do is when I'm given a chart like this, of course I don't want to memorize it, but the problem is that some people never look at the chart. They look at it once when they do the homework and never again. So when I was given a list like this, I'll tell you what I did. I would read through the list at least once a week. If you read through the list at least once a week, then you'll remember. You will remember. And it's not like I memorized it, you know, it's way too much stuff to memorize, but you'll remember because something will register in your subconscious about the property. And so fluorine, ozone, I don't know how to name that properly, you know, disulfate or something, S2O8, weird. Hydrogen peroxide, permanganate, lead 4 oxide, chlorine, dichromate, manganese 4 oxide, oxygen. What's IO3 minus? See, you reading the list, you're going to remember your nomenclature too. IO3 minus is periodate, iodate, iodide, hypoiodide. What is it? Iodate, good. Bromine, NO3 minus, everybody should know. NO3 minus is nitrate. Ag plus? Silver ion. You don't know how many people on the final exam write silver as +2. And so many people do that. It's a very common mistake. It's because people think in transition metals, all the transition metals are +2 and +3, but they aren't all +2 and +3, right? And so reading this, you know, is very useful exercise. And it's not rote memorization, it's just learning.
see. Because, you know, when you do that, you also look for patterns. And you'll see the patterns. Because the first time you read something, you don't necessarily see the pattern. But the 50th time you read something, you might see patterns come up. And then there's one more molarity problem here in blue.
The density of 3.30 molar potassium nitrate is 1.15 grams per milliliter. What is its percentage concentration by mass? That is totally new, right? I mean, that's not like any problem that's been discussed up to this point. And so what you'd look for is, you know, if the instructor is going to give a challenge problem, it might be something that you've never seen before, like this, you know. And so they could have assigned all the other homework problems, but didn't assign this one and throw this one out there, you know, making it difficult. And so what is the density of the, well, the density is given, and so we have the molarity. What is its, okay, so now what this is we need to convert molarity into percent concentration by mass. You have two choices here, and it depends on the instructor. One, the instructor likes to throw out challenge problems. They like to throw out problems that nobody's seen before, you know? And so if this wasn't one of the signed, this might be a good candidate for one of those challenge problems. Or two, the instructor just tests on what they talk about. Me, for Chem 4, I'll test what I talk about. Maybe I would throw in a problem like this on something else, you know, like a higher level chemistry class. And so, if you know, this is based on the instructor. You know, you got to know the instructor, and then you can figure it out whether you weight this or you don't weight this. For me, knowing me, I wouldn't weight this. So it's not that important because I didn't really talk about it. Like I said, you know, what I'm testing is just what I talk about.
But this is that one has some new twists to it for sure. Converting molarity to percent concentration by mass. And it's important. This type of problem you're going to be hit with in Chem 1A right away. This one, 53, when you get to solutions. But this is about as hard as it gets in Chem 1A, so we'll leave it for Chem 1A. So what did I say about molality? Let's take a look at the PowerPoint. What did I say about molality? Not that useful. Not as useful as molarity, because molarity you just go straight. You know, volume of solution, which is easy to measure, to moles. Molality is if you're given some sugar water, do you know how many kilograms of water you have and how many grams of sugar? No, you would have to separate the sugar from the water, because molality is not that useful because, let's show it. Switch. And so the disadvantage of molality is this. You need to separate the solute from the solvent. And typically we don't have it separated. The only time we have it separated is when we're making it. So if we're making it, then it's easy. You know, you just figure out how many kilograms of water you add to your sugar. And that's it. But if we know that, then we don't know the total volume. You know, we just add a kilogram, which is a liter of water to whatever sugar we have. But the main reason it's inconvenient is this, you know, if this is sugar water, how many kilograms of water, pure water, do I have? I don't know. I have to figure it out. I don't want to do that. And
And so this, typically this is given by the person who made it. Now, and then it's easy. And then, well, I can't ignore it completely because there are two things that molality is useful for. One has to do with temperature, and the other has to do with colligative properties. What did I say about temperature and molality? Yeah, it's not affected by temperature, so you'd go, okay, molality is not affected by temperature. Whereas molarity is affected by temperature. You know, volumes expand and volumes contract with temperature, right? There's no volumes. Masses don't expand and contract with temperature, so you don't have to worry about that. The volumes do. And what about colligative properties? Well, colligative properties depend on the molality, not the molarity. You know? And so we need to know the molality for colligative properties, but that comes later. And so it's not that useful, except, you know, it's temperature independent, which is an advantage. Yeah. But molarity, we're going to use far more, like 99% more than. And when we're dealing with solutions, we primarily use molarity, and then percent composition, and then molality. But molality calculations are fairly simple. We just need the grams, not the grams, the moles of solute, and the kilograms of solvent. So how many grams of potassium chloride must be dissolved in? So we have this many grams, so we know how many kilograms, and then it's 0.400 molal, so it's got to be 0.400 moles per kilogram. And so here we'll just use some dimensional analysis. We'll go from grams of water to kilograms of water to moles of potassium chloride using the molality. Molality would be 0.400 moles of KCl per kilogram of water. That would be the conversion factor required for this step here. And then the molar mass is required here for this conversion, so we get this to grams. So this is a molality calculation. Okay. So let's see the molality calculations in homework. Next. Well, before I spend all my time, I'm going to stop pretty soon because it's on this, and then we're just going to zip through it, but I'm just showing you what they do with the homework. And so here I'm on molality here, and I just look at the types of calculations I have. Calculate the molar concentration of a solution of 44.9 grams of naphthalene, C10H8, in 175 grams of benzene. So benzene is a solvent. Naphthalene is a solute. So I need moles of solute. So I go grams to mole, and divide it by kilograms of solvent. So I'll go grams to kilograms. So that's it there. Diethylamine is highly soluble in ethanol. Both of these hydrogen bond. Calculate the number of grams of diethylamine that would be dissolved in 4.00 times 10 squared grams of ethanol to produce 4.70 molal. And so here I know the ratio, you know, the composition. And so ethanol is the solvent, kilograms, and then I can figure out how many moles of diethylamine is required. How many milliliters of water are needed to dissolve 97.7 milligrams of sodium chloride in the preparation of 2.80 times 10 to the minus 3 molal solution? So all these are the same problem. They're all taking grams essentially to moles. To grams. And so I just make a note of that, and I go, oh, they're all the same problem, and there's no variation to that. So there is variation, but Krokolichi didn't have it because the problem in the book was different than those four. And
Those 4 were the same, or those 3 were the exact same problem. Okay, then we go to normality. What did I say about normality? Skip it. Skip that. Then we go to solution dilution. We did that. And we did an example of solution dilution. So go to 16. So skip normality. Go to solution dilution. There, solution dilution. So do you know this equation? Are you comfortable with this equation? If yes, then let's move to the problem. But volume times molar gives us what? Liters times molarity gives us, volume times molarity gives us moles. And so this is why molarity is so useful, because all we need to do is we can go straight from liters to moles. And so we have moles initial equals moles final. That's shown here in this slide. The moles of solute initial is equal to the moles. It's just the volume is different. Now this is much more dilute. Here's an example of making a solution. How many milliliters of commercial hydrochloric acid, which is 11.6 molar, should you use to prepare 5.5 liters of 0.500 molar hydrochloric acid? And so we're just going to use the solution dilution and solve for V concentrated. Solve for V concentrated, plug in all the numbers, and we get 237 milliliters. Okay, that was it for solution dilution. Then we look at the homework section here for solution dilution and see, what kind of variety we see in the types of problems.
Wait, why was it concentrated instead of dilution?
Well, they're asking how many milliliters of commercial hydrochloric acid? 11.6. So all I'm doing is comparing 11.6 to 0.500. And so I need 5.5 liters of 0.500. And so this might be the more concentrated, but it depends on this number here. Since this number is bigger, then I'm calling this the concentrated, because I'm comparing 11.6 versus 0.5.
So if we solve for dilution, we would get the same.
If we solve for, well, what we do is we just label it. Okay, the molarity of the concentrated is 11.6. The molarity of the dilute is 0.500. And so what we need is we need the volume of the concentrated and the volume of the dilute. What's given here? The volume of the dilute. We have 5.50 liters. And so the volume of the concentrated, we don't know what that is. And so the equation is VCMC is equal to VDMD. And so we solve for VC. And then we get this ratio here, which is MD over MC, the volume of the dilute. And it comes out to 237. So we take 237 milliliters of concentrated stuff and then dilute it to 5.5 liters. How much water is that? I don't know how much water that is. I guess we could calculate it, but we don't normally keep track. We just keep adding water until it hits the 5.5 liter mark. That's what's shown here. This person's not paying any attention to how much water, they aren't measuring how much water they're pouring in here. They're just adding until it hits the final volume. That's all they do. This is different than molality. If we're looking at molality, we need to measure how much solvent we're adding. We need to know how many kilograms of water we just added there. Otherwise, we can't calculate the molality. Either that or we weigh out the solute and then weigh out the total solution and then subtract the two to get the kilograms of solvents. Molality isn't as But we can still do solution dilution with molarities instead of molarities as well. Okay, and then we look at the calculations, because that's the end of the solution dilution. And so to reinforce, what we talked about in lecture, I would go to the homework next. After doing that problem, going to the homework next. And again, I wouldn't necessarily write. I think about this. Writing's good because in the future you can always revert back to it, because sometimes you forget, and so it's nice to have it written down. And so writing's nice, but sometimes you don't have enough time to write, so you just mentally think, can I solve this? If I solve this, what are the steps I take? If I can't solve this, could I solve it in a few minutes? And then I'll write it. If I can't solve it in a few minutes, then I'm just going to look at the answer, copy it down. What is the molarity of acetic acid solution? If 45 milliliters or 17 molar, so is diluted to 1.5 liters. And so we have the volume of the concentrated, 45, and the molarity of the concentrated, and we have the volume of the dilute, 1.5 liters or 1,500 milliliters, well, we're missing the molarity. It's the same type of calculation, it's just solving for one variable. How many milliliters, but it's different because we're solving for molarity rather than volume. How many milliliters? Okay, now we're solving for volume. How many milliliters of concentrated nitric acid, 16 molar, HNO3, will you use to prepare 750 milliliters of 0.69 molar? So this is just like the sample problem in the book. Just like the sample problem in the book. Skip it if you're comfortable with the sample problem in the book. Calculate the volume of 18 molar sulfuric acid required to prepare 3.0 liters of 2.9 normal. Well, this is a twist. Rather than having molar here, which would make it exactly the same as the problem in the book, they put normality, so you have to do one extra step. So this is an extra twist. So first we'd get the molarity and then convert molarity to normality. But do we have to worry about normality?
No, skip it.
So skip that. Calculate the normality, calculate the normality, skip that. And so, we see. All right, so hopefully that, you would just keep going through the same thing like that, and then you wouldn't treat or weight each of these problems equally, all 153. And so you could save a lot of time that way, I think. That's why I was asking. I was curious how much time you'd spent on this, because, and the same goes for reading too. If you do targeted reading, you could save a lot of time. And time is the most, time is the most precious thing, because there's not enough time. If everybody had enough time, everybody could do well. There's no problem with acing Chem 4. It's just everybody doesn't have enough time, however much that is, and people need different amounts of time. Their background, or their base knowledge, this how much you can.
So that was basically the review for chapter 16. Chapter.
Well, I didn't review. We can do just a rapid review here with chapter 16. Stoichiometry. This is one of the reasons why I didn't emphasize some of the earlier problems, because this is the first step in stoichiometry is liter to mole conversion. Liter to mole conversion using molarity. So it's easy to go liter to mole, mole to gram. That's this liter to mole, mole to gram, or liter to mole, mole to mole, mole to gram, or liter to mole to mole to liters of solution. Molarity. And so what we want to do is we want to see, stoichiometry is where you're going to see more variation. And so we have this one in ours, actually. But stoichiometry, you're going to see much more variation. So this is actually a good one to look at. So you want to do the examples that we did in class, and then you want to take a look at the homework to see, what kinds of twists can be thrown in there that might catch you off guard, or might be a bit of a curveball for you.
And so calculate the mass in grams of magnesium hydroxide that will precipitate from 25.0 milliliters of 0.398 molar magnesium chloride by the addition of excess sodium hydroxide solution. So, well, what do we do there? We have to, first, for stoichiometry, we have to write the equation, the balanced chemical equation. This is where it's going to hurt you a lot if you don't know nomenclature, because you don't know what magnesium, what is the formula for magnesium hydroxide? MgOH3? Actually, MgOH2. Well, you know, a lot of people will get this wrong. A lot of people write MgOH, you know, with all kinds of numbers there. And if you get that wrong, then unfortunately you don't get much partial credit because that's the first step. And so reviewing nomenclature, reviewing the ions is important. The thing that surprised me is this. You know, I told you a lot of people made the mistake of writing Ag plus 2 last semester. But I gave the chart out to everyone. And if I give the chart out to everyone, the AG's there. You don't even have to have it memorized. You just copy it off the chart, you know. And so watch out, because some people can be blinded, you know, by the test. They don't, you know, they get tunnel vision and they don't see what else is given. You could use any resources given to you, as long as it's given to you. Of course, you don't want to bring in others. But anyway, we get the equations down. So the equation is we want magnesium hydroxide. That's a product. We're going to form this from magnesium chloride plus sodium hydroxide. So we need the mole ratios here to make the balanced equation. We're also going to form sodium chloride. Here. So it looks like sodium hydroxide is 2 moles of sodium hydroxide to 1 mole of magnesium hydroxide. So it's 2 to 1 mole ratio. And so looking at this, I'm given the volume and the molarity. So I go milliliters to liters, liters to moles. So I get moles of magnesium chloride. From moles of magnesium chloride, so push the 1 to 1. From moles of magnesium chloride, I go to moles of magnesium hydroxide, 1 to 1 mole ratio. And then from moles of magnesium hydroxide, I would go to grams. That would be stoichiometry. Type 1, let's go to number 93. Calculate the amounts of calcium phosphate that will precipitate when excess sodium phosphate solution is added to 100 milliliters of 0.130 mole of calcium nitrate. Fortunately, these are all metathesis reactions. You know, calcium phosphate, I don't know, should I give you this chart? You know, for example, let me just tell you, last semester I gave this, sodium, I was very surprised because this is the first time it's ever happened to me. The first time it ever happened to me was over the summer, that somebody on the final exam wrote sodium as a +2 cation. And they wrote sodium chloride as NaCl2. I had to save that. So I still have that. But you know, they have this chart, and like I said, it's got to be tunnel vision or something. I mean, sodium's right there; it's +1. But what about phosphate? Well, that's maybe more excusable, phosphate, but not really. Because phosphate's on this chart. I mean, how can you not get phosphate? So people had phosphate with 3 oxygens. Some people had phosphate with 2 oxygens. Some people had phosphate with a -2 charge. Some people had it with, you know, and the thing is, it's right here on the chart. I didn't say you can't look at the chart. I mean, I gave the chart out for people to predict chemical reactions, right?
And so just be aware of that. And the thing is they probably only, I don't think they ever read through the chart even once. So they had no idea what was on the chart. Whereas people who read through the chart many times, this is simple, Perchloric acid, hydroiodic acid, hydrobromic acid, hydrochloric acid, sulfuric acid, chloric acid, nitric acid, hydronium, trichloroacetic acid, hydrogen sulfate or bisulfate, phosphoric acid. This one we skip, nitrous acid, hydrofluoric acid. You just go down formic acid, acetic acid, carbonic acid. So just reading through the chart once a week, I don't think they would have ever gotten the charges or the ratios wrong. I don't think, but maybe they still would have. All right. So going back to this, calcium phosphate will precipitate. So they're telling us as a thought. I won't tell you. You'd have to figure it out that calcium phosphates will precipitate. And so I might have asked, what mass of calcium phosphate would be produced, something like that. Or maybe I'll say precipitate. When excess sodium phosphate solution is added to 100 milliliters of calcium nitrate. So we go from milliliters of calcium nitrate solution to liters of calcium nitrate, liters to moles, moles to moles, moles to grams. So it's the exact same problem as number 91. We go on to 95. So what I'm looking for is variation. I want to see different twists to this. How many milliliters of 1.5 molar sodium hydroxide solution must react with aluminum to yield 2.00 liters of hydrogen measured at 22 degrees C and 708? Now this is a twist. This is quite a bit different. This is a combination of gas stoichiometry and solution stoichiometry. And so definitely a twist on this. So assume complete conversion of the reactant. So in this case, if you look at that reaction, that's a very strange reaction. That reaction there is a redox reaction, but it's a combination of redox and acid base there. And so they give you that reaction. That's not it. If you look at that reaction, what would you say? Just by looking at that reaction, I'd say, hey, that's a single replacement reaction, A plus BX, right? But it's not. You look at the product, so it's definitely not an A plus BX. Kind of, but not really. And so it's a more complex reaction, which we can break into simpler reactions. But it doesn't matter because they give us it anyway. And so anyway, what we have here is the gas. We have a volume of gas. So we go from volume of gas to moles of gas using molar volume, right? Or the ideal gas law. And from moles of gas, well, what is the gas? The gas is hydrogen. So we go moles of hydrogen to moles of sodium hydroxide. And from moles of sodium hydroxide, we go to liters of sodium hydroxide because we have the molarity, just invert molarity. And then from liters to milliliters. And so this is just a stoichiometry problem with one additional twist. We're approaching it from a gas. 97. What volume of 0.842 molar sodium hydroxide solution would react with 8.74 grams of sulfamic acid, a solid acid with one replaceable hydrogen? So what they mean by one replaceable hydrogen is this. We have 3 hydrogens there, but not all 3 are acidic. How many are acidic? Just 1, actually, right here. And so 1 acidic hydrogen. And so this is going to react with sodium hydroxide in a 1-to-1 ratio. This one is a bit more tricky. This one would be a significant variation because all the reactions I've given you are very straightforward, I think. I haven't given you reactions which are a combination of redox and Lewis acid base, nor have I given you reactions with acids that you haven't necessarily seen. This is what we call this is kind of a funny acid, sulfamic acid. Bizarre acid. This is a weird acid because this is also amphoteric as well, base. But and then how do you react it? Well, how you react it is you form sulfamate and
sodium sulfonate salt. And so this would be a jump, you know? And so, but think about the advantage that somebody would have if somebody had seen this for the first time on homework versus seeing this on the first time on an exam. You know, the person who's seen it on the homework first versus the exam is going to have a big step ahead. And so you know. And so in this case, I don't know what to do with sulfonate or sulfonic acid, so I'd look it up in the back, see what it is. Oh, that's how you do it, and then move on. You know, I wouldn't spend hours thinking, okay, how am I going to react this? You know, what's the formula for these? Okay, and then that's it. And then it goes on to the titration section, which is just more stoichiometry. And we did one titration problem, but there are other titration problems here. So I'd be looking at comparing the titration problem we did in class with the ones here to see what kinds of twists that the instructor can do. And the thing is, when you're at the UC, they try, you know, this is what happened to me. I got so used to it. I got so used to them trying to twist things around so that, so that the problems were tricky, basically. And so I was always looking for the tricks that they could throw out or the variations that they could throw out. I was never expecting anything straightforward. I was always expecting things that were, and that's the way I was trained. So when I first started, you know, I first started working at Santa Barbara City College, and so I wrote an exam, which was similar to the exam I would see at UCSB, but I got huge complaints from the students. You know, the students are saying, "What are you trying to do? Are you trying to trick us?" And I said, "Yes, I was trying to trick you." "Why?" they asked. And I said, "Well, that's the way I've always thought, you know, things. You know, because I always thought the instructors, my professors, were always trying to throw something that wasn't so straightforward, you know, something that was tricky." But then now it changed. I don't like I like just to see, you know. And so this is how I would study at UC. When you study for mine, you want to focus on the problems that we did in class. You know, you could, you know, seeing the variation will help you. You know, help you with the basic problems. But you want to do the basic problems. The one, like the examples I do in class. You know, are the most important. But anyway, learning the basic problems, if you know all these steps, and then you can get very comfortable with the basic problems. So when we go on to titration, you can look at the titration problem we did in class and compare that. Although I'm spending all my time on one chapter, what you want to do is you want to go back through your chapters 14, 15, and 17, and then tomorrow at the morning, whatever isn't clear or whatever is confusing, ask me tomorrow morning. But you should do your own review tonight. You know, go back through it. Depending on how much time you have, maybe you don't have enough time to go through and do everything. You know, but the time is, for at least for looking at the homework problems, this doesn't take much time. You know, what you're just trying to do is mentally come up with a strategy to solve it. And so we did the titration problem here. In this titration problem, we had to find the molarity of the acid. I did this as in one combined equation. Molarity is moles over liters. And so we want the molarity of the acid. So we want the moles of sulfuric acid over the liters of sulfuric acid. The liters are right here. If it gives us 25 milliliters of sulfuric acid, we can just convert that to liters. So we have this denominator. We just need the moles. The moles we're going to get from stoichiometry. And so this is a composite type problem, molarity and stoichiometry. And so the numerator, we do stoichiometry. That's what I did in class. And so the stoichiometry is, we go from milliliters of sodium hydroxide to liters of sodium hydroxide, liters of sodium hydroxide, moles of sodium hydroxide, moles of sodium hydroxide, to moles of sulfuric acid. Okay, I know we're out of time, but then you'd look here in the homework. And we make a comparison. The equation for the reaction by which a solution of sodium carbonate, so we give us the balanced chemical equation. The student determines
that 5.038 grams of sodium bicarbonate, or whichever, not sodium, acetic acid. Acetic acid uses 51.89. And so we look at all these problems and then see what kinds of variations they have here. And then titration using normality, we skipped that. Colligative properties of solutions, we did some of that. Then general questions, yes, we should do that. And the more challenging problems, yes, we should at least look at that. And by that time, the more challenging takes up a lot, but those would all be variations of the less challenging problems. So all these could be good, just one extra step thrown in there so you can compare. The more challenging you could say for later, what you want to focus on are the basics first, and then once you get the basics down, move on to the more challenging. Okay, anyway, why don't you review some of the other chapters, and we can continue with 16 if you want. You can take a look and see the specific things you want to discuss, or from the earlier chapters. But,
Thank you, sir.